Okay, imagine we have a site model like this, and we can start to do uh, site planning, right? So for site planning, the first thing you need to know. I think last week we have discussed what you do in site planning about the building mass and how you locate your building and your open space. Okay. So what you need to know, the first thing. Okay, maybe first I show you how did I derive this. Okay. So I think I have uploaded to Moodle an AutoCAD drawing. So you import the drawing, import the drawing. Huh? Where is it? Where is it? Oh yeah, this one, this one, this one. This is a large file, so it takes a while to load it. And also you have to make sure that your working unit is meter. One question, I mean, in the meantime, when it is uploading, anyone can tell me what kind of cloud service is this? Yeah, ruler. But then, go further. What kind of ruler surface? Is it developable? And you everyone agree upon this? Is this surface developable?
Can be divided into many lines.
No, developable means you can use a sheet of paper to cover it precisely. You think this is developable? Okay, first, of course, it's rule, right? Rule surface because it follows straight edges. Okay, and what is the condition of this rule surface be developable? There is something to do with the rules, right? What kind of condition it has to meet in order to have this rule surface developed? Three classes. And you have to think, are these rules belong to any of these three classes? The first class, all rules are parallel. They don't, right? The second class, all rules are concentric, which means they intersect at one point. That will make it conical surface, right? Are these rules going to intersect at one point? No. Okay? And the third class, all rule has to be the tangent of one curve, spatial curve. Apparently, no. So this surface is not developed. Okay? Theoretically, you cannot use a planar sheet of material to cover it. But technically, yes, you can. Okay, because in the real world, all material is somehow tolerant to twisting, at least a little bit. Okay, and if you are able to manage the tolerance, the possible tolerance of the material, then you can still build it using planar material. Okay? But theoretically, this is hyperbolic. You see, all these rules, they are not parallel, they are not going to intersect, they are not tangent curve of a spatial curve. Okay? Oh, it's done. Okay. So this is the model. And I mean, it's very comprehensive. Okay, it has so much information. Okay, but I think somehow the size of the text has to be modified. Right? Otherwise, these texts are not. I mean, the font of these texts are not adequate. Okay, but so but for people who knows Rhino very well, then they can make it. Okay. But anyway, you see, this drawing actually is drawn for people to read it manually. Okay? And how can we use computer program to derive the information that we want? First, we have to look at the organization of this drawing. And I think, I mean, it is from AutoCAD, from DWG file. I think the first thing I would look at is the layers. Okay, so you can see they still try to organize all the information in different layers, and they also very carefully code, use a way to code the name of all these layers. Okay, so this is a kind of clue that we can make use of. Okay, so for example, all the 3D building mass are from here to here. Okay, oh no, not this one, not this one. Okay, with the code 0000. Okay, so if you can check it by turn that off. Takes a while. Yeah, so all the 3D are gone. So now it's completely flat. Okay, so what we can do in Grasshopper, if we want to get all this 3D building mass, we use this pipeline. Okay, okay. Where you get this geometry, parameter geometry, and then here geometry pipeline. You click, then you get this component. Then if you specify the name of the layer, you can use wildcard. Okay, so you don't have to. I mean, there are dozens of layers, and all started with 00000, and then you use wildcard. Okay, for Rhino, you can also have names for every geometric entity. Okay, and we use wildcard, so it doesn't matter how it is called in its name. And then we can choose what type of geometric entity you want to retrieve. Here we only check mesh. Okay, so when I select this, you see all the meshes which are in layer started with 0000 would be included here. Okay, and okay, we can take a look at it. So they are all reference the mesh. Okay. And what I would feel like to do is you get it, right? And then you retrieve it. So we make a mesh. Where is the mesh? Where is mesh? Hmm. Here, sorry. Okay. You link to it, but it's still reference to the drawing, right? I would use internalized data so that this mesh are kept in grasshopper environment. And next time, if you open the Rhino with an empty drawing, you still get this information. Okay? So sometimes I like to do that because after a long time, you don't know which Rhino file is associated with this grasshopper file. Okay? And if you lost the Rhino file, then your grasshopper wouldn't work. So I would internalize all the critical input from Rhino so that next time I just need to open my grasshopper file. Okay? So this is the first thing that I want to retrieve. And what about this? Okay. These are lines which shows the boundary of every floor. Okay, so maybe we also need this. Okay, so I check the way they name the layers and then use this to take all of them, and they are lines. Okay, and I also internalize this. Okay, so put it here. And what are these 9310? Let's check the layer name. 93. Okay, they are not sorted, so let's sort. Nine three 9310. Temporary buildings. Oh, okay. They are 2D figures for all the buildings. Okay. Before 000, they are all 3D. Okay. But now this set of start with 93. Okay, start with 93. Let me see. 932. I would say I would take 932. Okay, because these are all the kind of thing that will block circulation. Okay. Sorry, this is in Chinese, so if you cannot read it, this is called door, this is fences, this kind of net, this is also fences, this is also walls, lower walls, this is also fences for construction site, different kind of walls, and this is temporary like a pavilion. Okay. And this is a wall-less building, temporary building under construction, and this is a permanent building. Okay, so all these lines show something that will block your circulation. So this might be of concern when we want to do some evaluation or analysis. Okay, so I decide to take this information and then put them all into this component. And what is 98101? Let me see. Okay, 98101. These are regarding the landscape. Okay, the height of the elevation of it, the contour lines. Okay, this this 9810102 and 9810101, they are contour lines. And then 9810200 are the mark of elevation. Okay, if we take a look at the drawing, wow, this is difficult. Okay, there are here at this corner, there are some contour lines. Okay, maybe we enlarge this area. Okay, and there are some, okay, here, this purple with this cross. So this is the point where they measure the elevation. So this is 47 meters above the sea level. And then they also mark the contour line with the elevation. So this is this mark the 45 meter, 44 meters. So every meter it has a contour line, and every 5 meters they use a different color to show it, and a different color and different layer. Okay, so that's the reason why the layers, there are two layers. Okay, one is for using cyan, and the other one is purple. Okay, so the purple line is every 5 meters. Okay, so these are the kind of information, and we can use a grasshopper program to transform all this contour line to its designated elevation, and then we can use that to build a three-dimensional landscape model. Okay. Okay, but I didn't do it for this one. Okay, because this site, which is quite far away from the site. I mean, this slope is quite far away from the site that we make our building. Okay, so okay, these are the contour lines, and what is it? This 97. Oh, the group start with 97 are the green area. Okay, this is the field, the open ground, the vegetable field, the fruit field, also the field, grass, bamboo, and forest. No, no, not forest, but a lot of trees. And these are the street trees. Okay, so all the 97 layers is regarding green area. Okay, sorry. So if we maybe we'll get information from this set of entities. Okay. And 94, what is 94? Okay, 94 are regarding street and road. Okay, but with this set, we are not able to analyze traffics, right? I mean, when we see this drawing, we know, okay, oh, here is a road and okay, whatever. But we cannot use computer program just like the one that we used last week, this Dijkstra algorithm to find the shortest path. So in order to do that, we have to edit, okay, or we have to draw the traffic network ourselves, okay? Okay, depending on the kind of tool that we use. Remember last time we used this, is this one? Yeah, Heteroptera, okay, to analyze the shortest path. But with this drawing, we have to do some work in order to make use of this function. Okay, so that's roughly about what we can do with Grasshopper and this drawing file. And now I don't need them, so I hide it. I hide all of them. Okay, and from there I chose 3 sites. Okay, let's start with this 3 sites. And I want to show you how I think we can use this Grasshopper process to build our log 100 model. Okay, maybe let's just take the first one out of it. Okay, which is this one. What is the first thing we need to know? The area. Okay, so we can calculate it.
Professor, could you use the bicycle?
Oh, okay.